Hi again everyone. In this video we're going to continue our look at Laplace transforms, and in particular we're going to discuss the first shifting theorem. Now the first shifting theorem provides a means of calculating the Laplace transform of functions that are of the following type. So you've got an exponential function multiplied by another function of t, which we'll denote by little g of t. Now we know that Laplace transforms are useful for solving initial value problems involving ordinary differential equations. And when you're solving these more difficult problems and more involved problems, the first shifting theorem comes up all the time. It's very useful within that context. So it's worth learning, and it's very powerful because it can help easily solve much more difficult problems. So let's have a look at what the first shifting theorem is. Okay, so basically the first shifting theorem says that if you take the Laplace transform of a function of this form, and if big G of s is the Laplace transform of little g, then what you do is you calculate this and then shift it a units. So that's where the shifting in the name comes from. The final answer involves a shift. And you may think, well, why is it called the first shifting theorem? Well, there is a second shifting theorem that we'll look at. But let's actually have a look at how to apply the first shifting theorem. So here we're asked to calculate the following Laplace transform of e to the 2t times t cubed. And we're asked to do it using the first shifting theorem. So the first thing we're going to do is compare this with this, identify a and little g. So a will be minus 2 here, and little g of t will be t cubed. So what we're going to do is calculate this first by calculating the Laplace transform of t cubed, and then we'll shift that to get our final answer by applying the first shifting theorem. Okay, so to calculate the Laplace transform of t cubed, we could do it by first principles, but I'm actually going to use a table because that is standard practice with Laplace transforms. So let's go down to our table. If we look down the left-hand column, then if m equals 3 in this third line, we're told that the Laplace transform of t cubed is 3 factorial over s to the power 4. So let's write that down. Okay, so you've calculated this part now. Let's shift this by replacing s with s plus a in brackets. So for our particular example, we'll replace s with s minus 2 in brackets. Okay, so now we actually have this right-hand side, so we can now apply the first shifting theorem. T. So you can see I've named the result or the theorem that I'm using to make it absolutely clear of my argument. Okay, so that's part A. Let's have a look at part B. Here we are asked to use the first shifting theorem to calculate the inverse Laplace transform here. So if you look back to our first shifting theorem, if I apply the inverse Laplace transforms to both sides, well, I can use that to calculate my example in part B. So let's have a go with that. So in the first shifting theorem, if I apply the inverse transform to both sides, I'll get the following. Now in our particular example, what we want to do here is identify this with G, big G of S plus A. So if I can identify A and little g, then I get my right hand side and I'll get my answer. So for our particular example, big G of S plus A is the following. So if A equals -1, replacing S minus 1 with S, I can get big G of S. Now, why did I want to do that? Well, to get little g, I need to take the inverse Laplace transform of this. Okay, so now I'm going to go back to my table and see if I can find the inverse Laplace transform of 1 on S cubed. Well, if I look down here and get to this third line, I see, well, it's going to be something like, for m equals 2, the inverse Laplace transform is going to be something like t squared. However, I have an m factorial here and only 1 here, so I need to divide by that for m equal to 2. So using the table, I can come up with this. And of course, it's just the following. Okay, so where to now? Well, to form this right-hand side, I just take what I've just calculated, multiply it by e to the minus at. So in this case, e to the t times this. And so, by the first shifting theorem, we can say the following. Okay, so I've done one example showing you how to take the transform and use the first shifting theorem. I've done another example showing you how to take the inverse transform and use the first shifting theorem. But let's have a look at the bigger picture. And basically these 2 points here have to do with method. So a good method for taking the Laplace transform via the first shifting theorem is to firstly calculate big G of S from little g of t by taking the transform of this, and then you shift G of S a units. And when trying to calculate the inverse Laplace transform via the first shifting theorem, identify A and big G of S from this, and then calculate little g of t by taking the inverse transform of this and multiply the answer, or g of s, big G of S, by this. Now here's some examples that I'm going to leave you with for you to work on. They're very similar to the example that I just solved, but what I'm going to do quickly is show you the proof of the first shifting theorem. Okay, so essentially I'm just going to work from first principles of the Laplace transform. So if I'm taking the Laplace transform of this function here, essentially I multiply by this exponential and integrate over this half line with respect to t. And now what I can do is actually combine these exponentials together and form the following. So you can see I no longer have just s here, I have s plus a in brackets, and that's just g of s plus a by definition. Okay, so the proof of the first shifting theorem isn't difficult, and hopefully you can see how the first shifting theorem is used here. Have a go at these examples. In the next video, we'll look at the second shifting theorem.